Alrighty, next we're going to talk about integrals of exponential functions. So let's think about the integral of e to the x dx. Now we know when we're taking integrals what we're really trying to do is figure out the derivative of what function equals e to the x. Okay, so that's what we're trying to do is figure out what function's derivative will equal e to the x. Well, we just learned in the last lesson that the derivative of e to the x is going to equal e to the x. So when we think about the integral of e to the x, we actually get e to the x. And then we have our plus constant because when we're taking our derivative, remember the derivative of a constant is 0. So the integral of e to the x dx is e to the x plus c. And if we apply the chain rule here, the integral of e to the u du is going to equal e to the u plus c. So it's going to be very important that if the exponent u here is a function, that the derivative of the function is also present in our integrand. Okay, so let's try our first example here. We have the integral of e to the 3x minus 1 dx. So here we can see that our u is going to equal 3x minus 1. And so we need to check our du. So the derivative of 3x minus 1 is going to be 3 dx. And then we simply check, do we have 3 dx up here? Well, no, we're missing a 3. So what we're going to do is place a 3 in here. And when we multiply by 3 in the integrand, we're going to multiply by 1/3 outside to balance it. Okay, so it's the same process that we've been doing over and over again. You got to make sure that that du is present in the integrand before you can use the integral equation. So now let's go ahead and use a u substitution here. So we'll have 1/3 times the integral of e to the u du. So we just grouped the 3 dx and rewrote it as du. And so this is going to be 1/3 e to the u plus c. And then we'll just back substitute in for u. So we have e to the 3x minus 1 plus c. Okay, now this u substitution is kind of an intermediate step, and you don't have to do it every time. If you can see that du is there, you can go straight to your final answer right here. All right, go ahead and try letter B on your own. Go ahead and pause the video, and then come on back when you're done to check your work. All right, welcome back. You should have let u equal negative x squared. And du then becomes negative 2x dx. And you can see here that we do have an x and a dx. And so what we have to add here into our integrand is a negative 2 multiple. And so we also have a negative 1/2 on the outside. I also want to point out that this 5 right here was not part of du. And because it's a constant multiple, we can just move it to the outside. Okay, and now we can see that we have du here. So I just used u substitution, e to the u du. The integral then is e to the u plus c. And then I back substituted u equals negative x squared in for u. And here is your final answer. All right, let's move on. Okay, in our next example here, we can see that we have a quotient here, but we always want to try to find our u du first. So in this case, I'm going to let u equal the exponent. Okay, so 1 over x. And let's go ahead and find du. Well, remember, when we have this, we change the sign, and then we raise the power here to 2. dx. And now I look, do I have u du in here? Well, here's e to the u, and then du, I have the dx, and I have the divided by x squared. The only thing I'm missing is the negative. So I just need to rewrite this with a negative. And then we'll put a negative on the outside to counteract that. Okay, so now we can see here that I do have the negative e to the u du. And so my integral is just going to be negative e to the u plus c, which is going to be negative e to the 1 over x plus c. All right, for letter D, I want you to try this one on your own. Go ahead and pause the video and come on back when you're done. All right, welcome back. You should have let u equal the exponent cosine x, and that makes du negative sine x dx. And you can see we have sine x and dx. The only thing we're missing is the negative. So we'll put a negative on the outside and a negative on the inside. If we use our u substitution now, we have negative integral e to the u du, which is just negative e to the u plus c, and then we'll back substitute our cosine x right in there. Now, our next example looks a little more challenging because now I have two different exponential functions here. So how do we know which one to let u equal? If we let u equal 2x, then du equals 2, and you can see we don't have that there. If we had just let this equal x, then dx would have been 1, and obviously we don't have that there as well. And so you can see that this, just taking u right at the beginning, is not going to be helpful. So when that is the case, we have to move to some other techniques, and what we're going to do is actually divide here. So this is going to become the integral of 5 over e to the 2x dx plus the integral of negative e to the x over e to the 2x dx. Okay, so just split that up into two different integrals, and let's integrate each one of these separately. Okay, and from here we want to rewrite these so that they look in our form e to the u du. So this first one, we're going to get 5e to the negative 2x dx. So the exponent just becomes negative. And then in this case, because we're dividing two bases of e, we have x minus 2x. So this is going to be the integral of negative e to the negative x dx. And now we can go ahead and use our integral rules here. So in this one case, u is going to equal negative 2x, and du will equal negative 2 dx. So you can see we're missing the negative 2. So let's rewrite this as 5 times negative 1/2 times the integral of negative 2e to the negative 2x dx. And for this one, since we already used u, let's go ahead and use v. We can use any letter there. And we'll just let that equal negative x. And so dv is going to be equal to negative 1 dx. And you can see negative dx is already there. So we don't need to rewrite this one at all. Okay, so let's go ahead and do our substitution now. For the first function, we're going to have negative 5/2 times the integral of e to the u du plus the integral of e to the v dv. And let's go ahead and integrate. So it's negative 5/2 e to the u plus e to the v plus c. And let's back substitute. So we have negative 5 halves e to the negative 2x, okay, because u was negative 2x, and then plus e to the v, and v is negative x, and then plus c. If you wish, you can put these negative exponents down, but it's not 100% necessary. All right, so there is our final answer. Again, the big concept here is if you can't just use substitution right away, you're going to go and divide this and then find each integral separately. All right, let's move on. Next, we want to find some definite integrals involving exponential functions. So here we have the integral from 0 to 1 of e to the negative x. So the first thing we need to do is find our u, which is negative x, and then our du, which is negative 1. So you can see we're missing a negative 1 here, so we'll put a negative on the outside and a negative on the inside. And so if we were to integrate this, now we have e to the u du, so it's just going to be negative e to the negative x. And we're going to evaluate this from 0 to 1. So we have negative e to the negative 1 minus negative e to the negative 0. Okay, and so here we're going to get negative 1 over e, and then the double negative will become positive, and e to the 0 is just 1, so plus 1. And if we were to calculate this, our approximation would be 0.632. All right, in our next example, here again we have our quotient, and so we can try letting u equal x, but if we did that, du would just be 1, and so that doesn't work. And also notice dividing here is not going to really work because the polynomial is in the denominator. So what we're going to do is we're going to try to let u equal the denominator. So this was another thing that we've done in the past, let u equal the denominator. And so du, in this case, what's the derivative of 1 plus e to the x? Well, it's just e to the x dx. So now, if I were to use u substitution, okay, do I have an ex d to the x? Yes, I do. So another way that we can think of this is u prime over u. Okay, now hopefully you've seen this before and can recall that the integral of u prime over u is just natural log of the absolute value of u, and we would evaluate then that from 0 to 1. Okay, so in this case, just because we saw e's doesn't mean that the exponent is necessarily going to be u. We might still use our natural log integration here. And we do that when we let the denominator equal u, and then du is actually in our numerator. Okay, so let's use u substitution here. So we're really looking for the natural log of the absolute value of 1 plus e to the x from 0 to 1. Okay, so we'll substitute in here. 1 plus e to the 1, and then minus the natural log, the absolute value of 1 plus e to the 0. And this is going to be positive, so it's just the natural log of 1 plus e, and then minus the natural log of, well, e to the 0 is just 1, so it's 1 plus 1, so the natural log of 2. Okay, and if we were to calculate this out, we would get an approximation of about 0.620. All right, so in analyzing letter h, we have the definite integral from negative 1 to 0 of e to the x cosine e to the x dx. So we see a lot of things happening here. I see a product, but I also see a composite function in that we have the cosine of another function. And so I'm going to think, let's try to let u equal e to the x. And then du would equal e to the x dx. Now, if I look at this, I do have an e to the x dx. So the function that we're really focusing on here is the cosine function. So this is going to be negative 1 to 0 of cosine u du. And the integral of cosine is sine. So we really have sine u from negative 1 to 0. And then we'll back substitute for u. So it's sine of e to the x from negative 1 to 0. And we'll use our fundamental theorem of calculus here and get sine of e to the 0 minus sine of e to the negative 1. And if we calculate this out, we'll get an approximation of about 0.482. Okay, so hopefully you've seen a couple examples where our u shifts. This one, it was an actual exponential function. In this case, we actually used the natural log function here to solve that. And then in this one, we were really looking at a cosine function. Okay, all three involving exponential functions, but all three solved in very different ways. All right, so that is integrals of exponential functions. All right, next we're going to talk about integrals for bases other than base e. So here, the integral of a to the u du equals 1 over the natural log of a times a to the u plus c. And you might also see this as a to the u over the natural log of a. And again, we can think about our integral of a to the u du as being the derivative of what function equals a to the u. Okay? And so we know that the derivative of a to the u equals natural log of a times a to the u. So how can I alter this so that it equals just a to the u? Well, you can see here that I would just divide by the natural log of a, and then I would be left with a to the u, which is what we're looking for. So that's why what goes in the middle here is a to the u over natural log of a. Okay, at any rate, let's go ahead and try some of these examples. So here we have the integral of 2 to the x dx. We still want to find a, our base is 2, and we need to find our u, which is our exponent, which is just x, and now our du equals 1 dx. So it's important when you're integrating that we remember that dx there. So do I see a to the u du? Well, let's see. So 2 to the x, well, that is a to the u, and then dx is du. And so I do see this function, meaning this is going to equal a to the u over natural log of a. Okay, and we can substitute back in now. So this is going to be 2 to the x over the natural log of 2. And don't forget our plus c, because this is an indefinite integral. All right, let's move on. All right, for letter b, we have the integral of 4 to the negative x dx. So again, a is going to be our base, which is 4, and u is going to be negative x, and so du in this case becomes negative 1 dx. And you can see here we have dx, but we don't have a negative, so that tells me I'm going to put a negative outside the integral, and a negative inside the integral. And now I have a to the u du. So our final answer here is 4 to the negative x, so a to the u, over the natural log of a, which is the natural log of 4, and then don't forget that negative that was out in front needs to continue there with us. So this is the negative of 4 to the negative x over the natural log of 4. Alright, let's take a look at letter C. Here I see x times 6 to the negative x squared, and we might think product rule right away, but let's check our a, u, and du first. So here a equals 6, u would equal negative x squared, and du equals negative 2x dx. Okay, so I see an x and a dx. All I'm missing is that negative 2. So we're going to rewrite this here as the integral of negative 2 times x times 6 to the negative x squared dx. And since I put that negative 2 inside, I'm going to have to put a negative 1/2 on the outside to balance it. So now if I used u substitution, I would have negative 1/2 times the integral of 6 to the u du. And if I integrate this, I'm going to get negative 1/2 times a to the u over the natural log of a. Okay, and if we just rewrote this, back substituting our c, we get negative 6 to the negative x squared over 2 natural log of 6. Okay, so that is integrals for bases other than e.